Let's talk chemistry with Pastor Dan. We're looking at two concepts today. The first is percentage error, and the second is graphing. So, percentage error is a way to determine the accuracy of a value. How confident are we of a value to what it's supposed to be? Now, the way that we find this, that little line means absolute value. So, the absolute value of TV minus EV all over TV times 100. Now, if you look at math terms, absolute value means the distance from the origin. If you want to be practical, all absolute value means is we don't have any negatives. The value is always going to be positive. Now, the value TV means true value, whatever we expect it to actually be. EV is experiment, what we get from doing the process of the lab or the experiment or the calculations, whatever we're doing. All right, so let's look at a problem. Okay, one other thing I've got to tell you. Accepted error is considered 10% or less. So whenever you're doing a lab report or a discussion or conclusion, if your error is less than 10%, you can say errors within acceptable limit. You're done, don't have to add in anything else. If, on the other hand, it's over 10%, you have to discuss it. Now, you don't ever want to blame yourself or your partner or the almighty grade giver. Now, your partner and yourself, you don't want to blame yourselves because you should have done the lab over again. You don't want to blame the almighty grade giver because that could hurt your grade. So you find some explanation for the possible error, conditions, instrumentation, anything along that line, but don't lie. All right, sounds good. Now let's try looking at a problem. Find the percentage error for your lab where you need to find the mass of 10.0 milliliters of water if the mass has been found to be 9.78 grams. Now, what we're going to do is find the density. The density is mass over volume, okay? So we have unknown mass, density rather. The mass is 9.75 grams, and the volume is 10.0 milliliters. So we're going to take and divide 9.75 by 10.0, and we get a density of 0.975 grams per milliliter. Now, what is acceptable? That is my EV. That's my experimental value. Now, what is the true value for water? Well, true density of water is 1.0. Now, that's actually 1.0000000. It's infinitely significant, so we're not going to ever worry about the number that way. So what we do is put the values in. TV minus EV all over TV times 100. So we're going to take 1 minus 0.975. Now remember, this one is significant. Last fill column is going to go to the tenths, hundredths, thousandths place, the third decimal. So we're going to end up with 0.0, so understand it's 0.025 grams per milliliter divided by 1.0000000 grams per milliliter. We only have two sig figs here because of subtraction, last fill column. We do that and then multiply that by 100 at the end. We're going to get 2.5% error. All right? There we go. Okay, now let's try another one. Find the percentage error of 67.98 grams a sample if the sample should have a mass of 78.99 grams. So again, start with our equation, percentage error, absolute value, true value minus experimental value, all over true value times 100. Okay, put our values. Our TV is 78.9 because it says the sample should have a mass of. The mass should mass at. So therefore, this is what it should be. This is my true value. We found it from the lab to be 76.98 grams. So we plug those values in, 78.99 minus 67.98, all over 78.98. When we subtract that, we get 11.01 last fill column for subtraction. Divide by 78.99 times 100. Answer is coming out 13.94. I have 4 sig figs, 11.01. I have 4 sig figs and 78.99. My grams cross out, so there's no grams. That's my error. Would this be acceptable error? No. Why? Because it's greater than 10%. Hopefully that makes sense. Now let's look at graphing. Now, what exactly is graphing? Graphing is a means of representing data in a pictorial form. Now, we have two variables that we always examine. The first one is called the independent variable, the variable that you control. The other is called the dependent variable, the results in the process. It's what we get as we do the experimentation. It's what we get from working out the lab. So, process itself. First step, the origin does not have to begin at 0, 0. Not a lot of people like to, but you don't have to. You can put down the values wherever you want. If you really, really want 0, 0, a lot of times you'll see it's people a little squiggly line, which means basically it's a break until actually things begin to get interesting. All right, then we have to make sure the graph takes at least half the graph surface. We don't want to leave empty space. So we don't want to put everything at one end or at the other end. We want to spread it out all the way through. Okay, show data points with geometric shapes. So if we put a point down, put some kind of shape. Now there's three main reasons why we do that. Number one, to prevent stray marks being identified. So we put a mark around with this is a data point. Second, that gives us a little range for error. This is a point, but it could be in here someplace. And third, by having different shapes, we could put multiple different graphs on the same expression. So we could have circles for one set of data, triangles for another set, squares for a third set of data, and be able to distinguish with each of them based on the shapes we have around them. Now, we draw the graph. There's two ways we can do it. We can either do exact fit, we can do best fit. Now, exact fit is point to point. Sort of like the stock exchange, up and down all over the place. We almost never do that. Best fit, on the other hand, is we do a general trend. That's either going to be a straight line or a curved line. Okay? So we always title it, final up. So that would be dependent versus independent. Okay? So here's a set of data. So this is going to be my independent because we have 5, 10, 20. That makes relative sense. Time is 6.25. These are my dependent variables. So we put them in. My independent is my x-axis. My dependent is my y-axis. So we get distance and time. We put our data so it spreads out at least half. So we have every 5, 10, 15, 20. And then I have my time factors are 1, 2, 3, 4, 5, 6, up to 25. I think it's 5 for every one of those. Graph my first point, and then I put a shape around it. Second point, third point, there we go. Looks like a straight line, so I'll make it a straight line. Then we have to title it. It's always dependent versus independent. So in this case, it's going to be time versus distance. All right, so here we go. Here is another set of data we have. All right, so we're going to set up my graph. My time is going to be my independent variable down here. My distance is going to be my dependent over here. Spread it between 1 to 7. Spread it from 15 to 75. We don't have to start at 0 here. So when we graph these up, we're going to start at 15 to 75. Goes like that. 0 to 7. Spread at least half the graph surface. We're going to get a straight line. I use triangles for my shapes around it. Okay? And then distance versus time is my graph. All right, so here we go. Two sets of information. Try these. First of all, try to find the percentage error for the first problem. Then after that, we're going to ask you to graph. Now, time is going to be my independent variable here. So time is going to be my x-axis. Speed is going to be my dependent variable. This has to be a y-axis. Try to graph those up. See what you come up with. Pause the video, work through it here, and then I'm going to show you how to do that. Okay, so let's look at the first one. For the first problem, we start with our equation. Plug it in. When we plug and subtract this through, and you actually need an absolute value over here as well. There we go. We end up with 1.3 grams per milliliters. Now it's only 2 sig figs because last filled column, that first decimal, that 2, goes to this 8, so as far as we can go, and it becomes, I believe, 1.314. That next number after is 5 or greater, less, so we drop it. So it's 1.3 grams per milliliter divided by 14.2 grams per milliliter. Grams per milliliter cross out. That'd be 9.2% error. If we were to ask if that's acceptable, in the conclusion we say that would be acceptable. So this here is my answer. And then for the graph, it should look something like this. We should have time on the x-axis, speed on the y-axis, and it should look like an exponential decay, so it's slowly moving down. And then don't forget the title of the graph, average speed versus time. All right, that is the end of what we have there, and hopefully you're doing well. And if there's any questions, let me know. Take care. Good night. Bye. God bless.